All right, let's go ahead and look at another example of geometric recursion. I've given you the pattern 80, 64, 51, and 41. And the question is this sequence arithmetic or geometric? Obviously, we're doing a geometric example, so it's geometric, but let's go ahead and understand why. So the first thing we have to remember is that geometric is an exponential pattern, and arithmetic is a linear pattern. And just by looking at the data, we can see that the gap from 80 to 64, if we do 64 minus 80, that shows us that we've decreased by 16. And then if we do that again and we subtract, we say 51 minus 64, that gives us a decrease of negative 13. It is not arithmetic because the gaps are decreasing. So we had a gap of negative 16, now we have a gap of negative 13. That tells us automatically that this is not going to be a linear pattern. So let's go ahead and let's look deeper into why it is a geometric pattern. So remember, when we are doing a geometric, we're looking for more of an exponential pattern, which means that we're going to be multiplying by the same value. So we are looking to multiply by a constant value. And so we have to find out what our multiplier is, okay? And in this case, our multiplier is what we call a common ratio, okay? So how do we do that? We just simply take term 2, or we take the second term or the one that we have, and we're going to divide it by the previous term. Term 1. So we can do that. We can make sets of these. So let's go ahead and do that. Let's take a set here. We're going to take the second term. We're going to divide it by the first term. So 64 divided by 80. And then we make another set out of this. We take 51 and we divide it by 64. And let's go ahead and make another set. But what we want to do is we want to make sure they're right next to each other. 41 divided by 51. Now, when we do this, we're just going to go ahead and make sure that our multiplier all works out the same. So let's go ahead and type this in. We have 64 over 80 was one of them. 64 divided by 80, we get 0.8. Let's go back. We get 51 over 64. So 51 divided by 64. There's 0.7968. That also rounds to 0.8. And let's do 41 over 51. 41 over 51. Guess what? There's 0.8 again. So it looks like every single time we do this, we are going to get a approximately a multiplier of times 0.8. So we're going to be multiplying by 0.8. So our common ratio is simply 0.8. And what that means is we are keeping or retaining 80% from one value to the next. So now let's go to our recursive formula. Okay, we found our common ratio. We've decided that we're multiplying by 0.8 every single time. Now what we're going to do is we're going to go to our recursive formula. And when we start our recursive formula, we always start with the initial point that we're given. So let's go ahead and label it. This is the first point in our sequence, the second point, the third point, and the fourth point. And what we just simply do is we start by saying our first point is 80. So I'm going to write a sub 1 equals to 80. That is our initial point. And then what we're going to do is we're going to tell what we are doing to that first point. And how we do that is we just simply write a sub n. And what that pretty much means is in order to get to the next. I'll write that right there. That's in order to get to the next point. We're going to take what we have, an minus 1. Okay, this is what we have now, which, by the way, is 80. Okay, and what do we do to it? We multiply by 0.8. So I'm going to say times 0.8. Okay, so times 0.8. And all that means is in order to get to the next point, we'd take the 80, we'd slide the whole value right here, and we'd say 80 times 0.8, and that would give us this 64. And we'd follow that pattern. So this is our recursive formula, where we just simply take a sub 1 equals 80, a sub n equals a sub n minus 1 times 0.8. We did say that this is a recursive formula, And it is an exponential that would model this. So what we're going to do now is we're going to go ahead and write the explicit formula. Whoops, I put a T on there. We're going to write the explicit formula for this. And the explicit formula is the exponential equation. So the y equals a times b to the x. And we've already talked about exponentials. This is our multiplier. Okay, and this is our initial. But remember, it's our initial value when it is the y, when it is the y-intercept, or when we're at x equals 0, or the term is equal to 0. So we've got to do a little bit of manipulation in order to get our exponential equation out of this. So first of all, we know our multiplier. So let's go and fill things in. A, b to the x. Our multiplier is 0.8. And the one thing we have to do is we have to determine a value, which is when x equals to 0. Well, check it out. We have term 1, we have term 2, we have term 3, we have term 4, but we don't have term 0. So we're going to find 0. Okay. Well, think about what we've done. In this direction, we have multiplied by 0.8 the entire time. Well, how do we go back a step? Well, if I want to go back a step, we have to do the inverse of multiplying. We have to divide by 0.8. So what we're going to do is we're going to take 80 and let's just divide it by 0.8 to get our 0th term. So let's go in and do that. That's 80 divided by 0.8, and that gives us 100. And so I'm going to put 100 here. So now we can finish our explicit formula. The a value, which is the 0th term, which is right there, is just simply 100. So our equation would be y equals to 100 times 0.8 to the x, and that would be our explicit formula. All right, y'all, I hope that helps you out with geometric recursion.